expected to grow. The afternoon will be about technologies that will help them grow sustainably. And we have 6 speakers again. The first topic will be on the key role that instrumentation and sensors play in gathering the data we need. And the speaker is Sloane of Planet Ocean.
Thanks, Gus, and thanks IMarEST for volunteering me to give this talk today. I do have a bit of a cold, so I apologise in advance for that. So basically what I wanted to do is talk about sensors, but then it occurred to me that I couldn't really do that in isolation, otherwise it would look like a catalogue of sensor technology. So I'm trying to put it in perspective to other things. It's certainly the morning speakers have made that a little bit easier for me because I could look into some of the things they've been talking about. I'm going to start at the end of the story and work backwards. So what most practitioners are used to, I suspect, is working with information and viewing it in process forms from a variety of sources. And it's important, I think, for us all to just take a step back and revisit where that might come from, where that information comes from. Before it even gets to that stage, it will have been transmitted around the world using all sorts of technologies, including wireless and radios and satellites and internet, all sorts of electromagnetic and optical methods for transmitting the data around. And at some point on that journey, hopefully it will have been quality controlled and archived somewhere, so that by the time it gets through to the data preparation and the information, it will have some controls placed on it. Before it even gets that far, it will have been collected by real things, by real people in the field, and clearly there's a variety of platforms, just a few here: research vessels, data buoys, aircraft, terrestrial stations, platforms of opportunity, and seabed moorings and dips. And it's all too easy when we're working with big data and big information packages now to forget that somewhere along the line there are people out there getting cold and wet, gathering that data for us. Methods being used for many, many years, well known and well understood, but the science of the sensor is still very much an important aspect of those things, because on each of those platforms will be an instrument. On each of those instruments will be one or, in fact, multiple sensors. We've heard a bit already about autonomy, and that's certainly the big driver for a number of reasons currently. It's trying to lower the cost of each data point that we acquire. That places specific demands on sensors and sensors designers and manufacturers, and you can see there a few examples. One of the most innovative there perhaps is the SEAL system, which is an early form of autonomous underwater vehicle, a bit difficult to control, but it does gather very good data very cheaply, so it's worth considering. We've heard a variation of this before today. You can't manage what you can't measure, and again, I'm trying to underline here things which we should continually reference in our day-to-day work. The sensors that we deploy, particularly under the ocean, are subject to some really extreme environments. The lander there from NOC in Liverpool sits on the seabed 4,000 odd metres for a few years at a time, gathering data and releasing pods to the surface to get that data away to those that need it, and that in itself is not an easy task. We're looking at very corrosive seas at the moment, increasing pH levels. We're looking at very cold environments, and we're looking at increasing very hot environments around 400 degrees C on a hydrothermal vent, for example. So getting sensors that perform the function properly, not always the easiest thing you can do. So who decides what we measure? Which is an interesting question. And in terms of marine science, there are various bodies that convene to decide these things. And one of those is GOOSE, Global Ocean Observing System, and with various expert panels in various disciplines, they've come up with a series of things that they'd like to measure. And that is assessed by these groups into just how feasible is it to measure those things and what the impact of those things, of those measure-rounds would be. And clearly not all of those fall into that nice blue box at the top right there. So things which are feasible to measure and have a massive impact. And of course cost comes into that. And the question there perhaps is, what don't we measure? Will it cost the Earth? Is that in terms of expense, or if we don't measure it, will it cost the Earth? So let's have a quick look at current sensor technology before we go on to looking forward. It's important, I think, to continually remind ourselves that all sensors are not equal. And each of these examples, the one on your left is for fisheries, for biological monitoring. One on the right is mainly for physical oceanography. Both measure exactly the same thing: conductivity, temperature, and depth, to give us salinity, speed, sound, density, and those sort of things. Each has its place, and one is not better than the other at doing their associated tasks. But when you're looking at data, it's important to remember what was used to acquire that data. So if you're looking to produce some physical oceanography data, and the only data set you can get is from a biologist, then you need to recognise that, and it needs to be acknowledged in the metadata. It's also true to say that if at all possible, we encourage that you use the best instrumentation possible. Now, if you're a biologist and you can get away with an instrument which costs maybe £500, that's a big argument. But if you've gone to the trouble of acquiring that data, which is often the most expensive phase, so you're putting the instrument in the water, getting it out of the water, processing the data, you may as well deploy something which is better than you need, because in 10 years' time, 20 years' time, somebody may want to come back and use that data. And so if you've measured to the best of your ability, often financial ability, then you're doing a good service to the sector as a whole. So I'd encourage people to consider that when you're planning measurements. In recent years, there's been a big move towards use of optics in sensor technology, and for a variety of reasons. It's low power, it's accessible, it's well understood, and there are various standard instruments now which use fluorescence and reflectance and absorption and various other techniques. And we continue to see developments in this area. Sensors are becoming more combined, so multi-channel instruments on one payload, or different measure-rounds being made using optical techniques. They're particularly useful in deployed systems that go down for long periods. They're relatively stable, assuming you can keep the optics clean, which is often the challenge. This is a picture we've already seen once today. I expect Russ may show it later, I guess. But of interest is on the bottom left there. So this is the autonomous fleet that exists at the NOC in Southampton. So that's their range of autonomous data collection platforms. I think it's quite an old image now, and there's probably several more platforms available. And the team at the NOC Census group have tasked themselves with finding answers to those sensors there, the nitrates, phosphates, silicates, ammoniums, and so on, that they can put in these gliders, particularly the gliders, but also in the AutoSub AUVs, and that's been their driver. And those parameters have come from that Goose work earlier on, and they found a way to make those measurements feasible in those platforms, which is quite a challenge. So just to I won't run through in any great detail, but basically we're talking here microfluidics. So it's an optical measurement at the end of the day, but essentially we're taking, they are taking reagents from packs, doing wet chemistry in the field. It's using standard lab techniques that they would use in the lab, using a microfluidic sensor, which is this chip here, etched or milled, and little channels that mix the reagents and the sample together, and then optically, colorimetrically often, to assess that and reveal the concentration of the particular thing they're measuring. Can be used for a wide range of measure-rounds, and has proved to be very, very successful down at great depths too. It's still using mechanical parts. We've got pumps and bags full of reagent and so on. But it's a method. It fits that cost-benefit block very well, and it's proving to do some very good work, very good science. A little bit more detail of it there. You can see it's quite small, but still a very powerful piece of kit. Same group, in parallel at the moment, are developing sensors which don't use reagents, and that's a big advantage, as you can imagine. The reagents have a shelf life, and they're not really suitable for long-term deployments on packages. So this is a sensor which has been developed for methane, and it uses refractive index technique. So without going into too much detail, there's a gold film which is processed to attract a single molecule, and that changes the refractive index, and the light, again optical measurement, hits a different part of the sensor, and it gives you abundance measurements. So already we're seeing a move away from wet chemistry but addressing these difficult to measure challenges. Project is quite well advanced. That's the sort of scale of things. It will be going in the water next year to measure methane, which is an important parameter for oil and gas in particular. So it's quite well advanced and under continuous development. Strangely, although it's not even been completed and in the water yet, it's already being outpaced, and this is an indication of the pace of change in sensor technology. Same group, different scientists. So a very similar process. In fact, it's a variation on the theme. So instead of having the gold outward facing to the water, the gold now wraps around a fibre optic, and likewise it will change its refractive index based on the molecules it latches onto, and that can be measured. Beauty of that is, of course, it's much smaller, and you can process and lay out multiple fibres on a single small chip. So this is still on paper, but I'm guessing that chip will be something of that size of a postage stamp. Target price about $90. So disposable technology, and with relatively long deployment capability, down largely to the equipment that surrounds it. But you see there, you can measure a large number of variables on a single chip, and that's very important. The ability to leverage the best out of your platform is becoming something that's talked about quite often. So the expensive AUV or glider or mooring or whatever, we want to get as much from that as we possibly can by loading it up with as many sensors as we can. And this kind of technology lends itself very well to that. As well as the science community asking for particular things to be measured, it's true also of the commercial world, and certainly the oil and gas sector has been active in looking at things like methane, and that's been a big request from them. But they're also now asking to look for the long train aliphatics, the ethanes and propanes and those kind of chemistries, which companies like Blue Ocean Ltd and the commercial oceanography companies are willing to address, and they're not in a position to want to wait for science developments to escape from research labs. They're quite keen to get behind that to stimulate that development. Can't go on too much further without looking into the future, and this surprised me when I revisited it, to be honest. My company was involved at the very early stages with a team from University of Sussex who met with us and suggested they might have a quantum sensor for us. So that got us all going, well, okay, what's a quantum sensor? You know, how can that be when these things are not really understood? And we went and we had a look, and they had a laboratory about, I guess, the size, this sort of size here, full of optics workbench, laser heaters, laser coolers, all sorts of gadgetry which nobody really understood, and they were quite confident that they could produce a sensor. We were looking at magnetometers at the time for pipeline location and tracking. And so we all shook hands and nodded and said, well, we will see you in 20 years, and off we went. But then I got in contact just recently, and it turns out they've already got this thing working in something that size. So that's probably the size of a suitcase. Okay, so we're not really looking in cloud cuckoo land, if that's my wife to know. If we're not in cloud cuckoo land, we are now looking at quantum technology in the real world, and that will bring quite dramatic changes. If you look here at their development timeline over just a few years, it is quite significant. And this is all going on in the background. We've yet, and this isn't the only group that's working on quantum sensors. We've been quite reasonable, I suspect is a bad word, but it's the only one I can conjure up in our request for magnetometers to look at pipelines. The technology that they're developing has very far-reaching possibilities. They can map the seabed very easily and very quickly from a magnetosphere point of view and detect objects that shouldn't be there from space. So it could change the whole face of remote sensing in the not too distant future. I can't escape from mentioning meteorology. This is, after all, the Met Ocean Operation Oceanography SIG. My observation, having spent 3 years in meteorology, it hasn't moved very much. In my opinion, somebody will shoot me down, I'm sure, at the panel. But that's the old Munro head unit. I say the old Munro head unit, it's certainly around in the war, and actually it's still being produced for some users. Really, that was the next major leap. Back in probably the late 80s, early 90s, in separate coupling sensors and vanes, which were accepted by Met Office. I think that's the key thing. And then 2 ultrasonic sensors for high resolution turbulence measurement. They're becoming more common now. And then combined systems, which we see regularly now on platforms to gather temperature, pressure, humidity, rainfall, solar radiation, all in one package. So not the same kind of leaps forward as we've seen possibly in the oceanography world. The biggest single change in the world of meteorology is perhaps floating LiDARs, or LiDARs in general. These are up-looking laser systems which scatter apart from particles in the atmosphere, and looking at the reflectance you can determine wind speed and direction. The driver for that is purely economic. If you look at the Met mast in the background there, which was traditionally installed in a potential wind farm site to gauge the wind speed and directions at various altitudes, so you can calculate not only productivity but loading on the turbines. £10 million was the last estimate I got, something of that sort, a lot of money. It goes in, it's in there for good, it can't move it around. And then LiDAR technology became more affordable, became able to be fit on relatively small buoys, cost saving of 10 to 1, and a no-brainer really for that industry. It took a while for that technology to be trusted, but it's now routinely used and can be moved around very easily. So back to what I know most, smart sensors and smart oceans. I just wanted to refer here to how sensors are being used on ocean observatories and other sort of fixed installations, and there are a few of those around the world. Perhaps the best known is the Venus and Neptune observatories in Western Canada, North America, which has been used and in place now for several years, and has the ability not only to produce real-time oceanographic data from a cabled observatory, but also to be used as a test bed for sensor manufacturers and investigators to put sensors on to evaluate them against references that are already there. So two very important uses for these fixed observatories. One thing that we shouldn't forget is who qualifies these sensors, who says that they're fit for purpose. Well, in the water industry, you've got this thing called MCERTS, and that's an Environment Agency initiative, really, which is designed not only to assess and certify for use sensors or instruments, but also personnel, procedures, whole companies. So there is a structure there which we don't really see in oceanography. And I don't know whether that's a good thing or a bad thing. It might inhibit sensor development, I don't know. There is this ACT, which is in the States. It's a voluntary organisation. You can submit your instruments for evaluation by them, and they will do independent testing at a variety of sites in different conditions, and totally independently, and they'll publish that information. But it's, I think, somebody might correct me, but I think that's about as close as we get to a standards, independent standards assessment body for I wanted to just touch on citizen science because this involves sensors. As you may or may not know, the Met Office have their WOW system, weather observation website, where they empower everybody essentially to make weather observations, and using a little app you can upload your observations to the website. And that can be from a really enthusiastic amateur to just the average chap in the street. And you might think, well, that must give some horrendous data. But because of the number of observations that are being made by the public, they're able to statistically work on that data to filter out the outliers and so on, and get actually very good background data, which helps their certainly hindcast models, but probably the forecast models in the future. So it's something which we don't see a lot of in oceanography, but I suspect we will in the future. Certainly there are some initiatives already, this coastal citizen science initiative, which is already out there, and it's something we need to be aware of that's coming down the pipe. If we're talking about operational oceanography users of data, where the data might be sparse from an official source, but there's a need to use it. This is something which is soon to be upon us. So these are sensors that can be installed in surfboards, so that data can be collected from beaches where people are surfing, clearly for water quality points of view. There is a group in Australia that producing a small sonar system which can be fitted to detect sharks and then provide an early warning. Certainly not for the guy that detected it, but maybe one or two others down the line that would benefit from that information. So we can see even in our world citizen science becoming increasingly popular. I saw, I think yesterday on the news, there's a small ocean colour monitor now, which you can plug into a smartphone for making ocean colour monitor measurements, which is really quite interesting. Probably quite a high quality sensor, but I would be very surprised that if not in the next 5 to 10 years we didn't see a range of ocean sensors that we can connect to our smartphones to contribute to the ocean observations. As long as we know what the accuracy and what the reliability of those sensors are, it doesn't really matter. More data is quite useful. I wanted to just say a little bit about changes that are going on. So sensors can be easily distracted. So in our striving to measure weird and wonderful things, we often have to compromise, and nitrates is a good example. So this is a nitrate sensor. It's a UV spectrometer essentially, but the problem is it also measures all sorts of other things that you don't really want it to. So there's an awful lot of effort, perhaps more effort goes into discriminating the signal you want from the signal you don't want, and that's true for a lot of sensors. I remember a long time ago, the first inductive conductivity sensor I designed, it worked really, really well as a pressure sensor. So as soon as it went down to depth, it was compressed and made marvellous measurements of pressure as well as conductivity. So there's a lot of work going on now on some of those methane sensors and the long chain artifacts that I talked about earlier, which are really, really species specific, and we'll be able to see a lot less fiddling, let's say, with the data in the new brands of sensors that are coming along. I've mentioned already how important it is now to asset squeeze the platform. So smaller sensors that are capable of measuring multiple parameters without being influenced by other sensors are very much the thought process now of people that are designing sensors. So we've got all this sensor technology evolving. I've quickly looked through that without going into too much detail, but it did lead me to question what do we do with all this data? So the average Formula One car has, I spoke to a mechanic at McLaren, he wouldn't tell me too much, but he said about 200 sensors on the average Formula One car. And that gives rise to 3 terabytes of data over a full race. You multiply that by 20 cars in 90 minutes, that's an awful lot of data. Now they've got teams of guys that looking at that, not just at the track side, but back at base too. But that's a lot of data, and I think one of the things we have to ask ourselves is, do we really want all of that data from all of those data points? This is the Argo float network. For those of you who don't know, this is an Argo float. They're deployed for a few years at a time. They go up and down using a buoyancy engine. They accumulate data and transmit that data when they get to the surface. And it's been a real game changer certainly for Met Ocean type projects. And there are at any one time, 3,800 of those bobbing around in the ocean at any one time. If we were to get the 3 terabytes of data per message, we'd be swamped. Just wanted to quickly say then, so data overload, there's Macondo. Immediately after that, we had 140 aircraft in the area, 6,000 vessels, and 40,000 data samples. You've got to wonder how we can process that data. The way to do that is convert it to information and just provide traffic light systems. You have to know what the sensor was doing before you rely on that traffic light data. I think John showed this slide earlier. That took 35 years. That's 35-year history of the development of the cell phone. We've gone from something which was big but lasted for 5 or 6 days on a single charge to something which is small, which runs out in half a day, and now we're going big again. So it's really difficult to project where we're going to go. But if you look at the same 35-year timeline on a quantum sensor, I'll just leave it to your imaginations really to see where that might take us, particularly in our field. I'm going to skip over that because it's controversial. So, and Gus is winding me up. So just to put things in perspective, if we're relying on AI, we've heard that several times today. We're relying on AI to inform us. We've got to be sure of the information that's being fed to those systems, which machine learning too. But also we've got to protect our data. It's open source, open information is great, but it can be weaponized. Let's not forget that. So we need to be careful about how this data flows. Thank you very much.